Good morning. Myself, K.N. Sridhar, Assistant Professor of Physics, Government First State College, Kolar. Now, I am taking the magnetic field and forces of second BSc, third semester, Bangalore North University Physics, in which we are studying force on a moving charge in a magnetic field. A charge, we are considering a charge Q. A charge Q is considered, and this charge Q is assumed to be moving with a uniform velocity V. Is assumed to be moving with a uniform velocity V in a magnetic field P. V is the magnetic field in which the charge Q moves with a uniform velocity V. If that is the case, then the charge will experience a force Fb. F represents the force and the subscript B represents the force due to the magnetic field, due to the motion of charge in a magnetic field B, hence Fb. And this force experienced by a charge Q moving in a magnetic field B with uniform velocity V depends on the magnitude of the charge. It depends on the magnitude of the charge, that is F is directly proportional to Q. It depends on the magnetic field. It depends on the magnetic field, that is F is directly proportional to B, and it depends on the velocity with which the charge is moving. It depends on the velocity. Therefore, the force experienced by a charge moving in a magnetic field with a certain velocity depends on the magnitude of the charge. It depends on the magnitude of the charge. It depends on the strength of the magnetic field, and it depends on the velocity with which the charge is moving. So combining all these three, we get F is equal to, or Fb equals Q into V cross B. We get this expression. And this is the force experienced by the charge Q moving in a magnetic field B with a velocity V. And this is the vector form of force experience. This is the vector form. Or this can be rewritten as Fb equals QVB sine theta. Fb equals QVB sine theta, where theta is the angle between the velocity vector V and the magnetic field vector B. Theta is the angle between V and B. If theta equals 0 degree or 180 degree, so we have a special case. If theta equals 0 or 180. Theta equals 0 in the sense, let this is the magnetic field. I am representing magnetic field lines, the parallel lines. Let these are the magnetic field lines. If these are the magnetic field lines, the field is said to be uniform. Let this is the magnetic field in which the charge is moving. Let this is B. And if a charge is moving in this direction, then theta will be 0. If this is Q, then theta will be 0. If this is the direction of motion of the charge Q, then theta will be 180 degree. Here theta is 180. And here theta is 0. If the charge is moving parallel to the magnetic field, then theta is 0. If the charge is moving anti-parallel to the direction of the magnetic field, then theta is 180 degree. In both the cases, sine theta become equal to 0. Sine 0 or sine 180 will be 0. Therefore, Q into V into B into 0 will become equal to 0. Hence, charged particle moving parallel to the direction of the magnetic field does not experience any force. Similarly, if the charge moves at right angles to the magnetic field, if this is B, and if the charge moves at right angles to the magnetic field, and if this is the direction of motion of the charge, then theta will be 90 degree. If that is the case, sin 90 is 1. Therefore, FB equals QVB into sin 90 is 1. Therefore, this is the maximum force that the charged particle can experience. Hence, the charged particle is said to experience a maximum force of QVB when it moves at right angles to the magnetic field. When it moves at right angles to the magnetic field. Similarly, if the charge is at rest, if V equals 0, then the charge is said to be at rest. Therefore, Q into 0 into B sin theta will become equal to 0 because V is 0. Hence, a charged particle at rest will not experience any force. Now coming to the Lorentz force, it is the resultant force experienced by a charge moving in both electric as well as magnetic fields. It is the resultant of the forces experienced by a charged particle moving in electric as well as magnetic fields. And therefore, F is nothing but equal to Fe plus Fb. Fe is the force experienced by the charge moving in the electric field, and Fb is the force experienced by the charge moving in the magnetic field. Right. Now, if let Fe is the force experienced by a charge Q when it is moving in an electric field, or when it is in an electric field. E is the electric field in which we have considered a charge Q. Therefore, the force experienced by this charge when kept in an electric field E is F is equal to Q into E. F is equal to Q into E is the force experienced by the charge kept in an electric field. I take this as Fe. Instead of F, I call this as Fe because it is the force due to electric field. Fe. Now, let Fb is the force experienced by the charge Q moving in the magnetic field B with a velocity V. Then the force experienced is Fb equals Q into V cross B. This is the force experienced by the charge moving in the magnetic field in the vector form. The resultant is the Lorentz force. It can be represented by F or Fl. Now, the net force experienced is F is equal to or Fl is equal to or simply F is equal to Fe plus Fb. Fe is nothing but equal to QE Fe equals QE and Fb equals Q into V cross B. So we have taken Q common, and it is therefore equal to Q into E plus of V cross B. Now, if the charge is moving at right angles to the magnetic field, then this is the maximum force experienced. Charge moving at right angles to the magnetic field. Fb is the force experienced, which is given by QVB sin theta become equal to 1 because theta is 90 degree. If that is the case, in this expression, if I take Q equals 1 coulomb and V is equal to 1 meter per second, then Fb is equal to B. By making use of this, we can define the magnetic induction B. The magnetic induction B is numerically equal to the force experienced by a unit charge moving at right angles to a magnetic field with unit velocity. B is equal to Fb. B is equal to Fb, that is, magnetic induction is numerically equal to the force experienced by a unit charge, moving at right angles to a magnetic field with a unit velocity. This is how we define magnetic induction B. The unit used to measure this magnetic induction is Tesla or Weber per meter square. Tesla or Weber per meter square is the SI unit used to measure the magnetic induction. Magnetic induction in a uniform magnetic field is said to be 1 Tesla, or 1 Weber per meter square if a charge of 1 coulomb moving at right angles to the magnetic field experiences a force of 1 Newton. Magnetic induction in a uniform magnetic field is said to be 1 Tesla or 1 Weber per meter square if a charge of 1 coulomb moving at right angles to a uniform magnetic field at a velocity of 1 meter per second experiences a force of 1 Newton. If it experiences a force of 1 Newton when it is moving with a velocity of 1 meter, when a charge of 1 coulomb moving with a velocity of 1 meter per second, then the magnetic induction is said to be equal to 1 Tesla or 1 Weber per meter square. This is about the Lorentz force, about the definition of B. We stop here.